Greetings YouTubers, and welcome to episode 8 of my ongoing series, Lies That Flerfs Tell. Today we're going to take a second look at Nathan Oakley's vacuous claim, Earth measures flat. As I discussed in my last video, this is just a mindless and completely unsupported religious dogma. It's a 3-word slogan that his cult members can shout while sticking their fingers in their ears whenever anyone asks them for evidence supporting their beliefs. Last time we looked at Oakley's fallacious claim that the construction and measurement of elevation angles somehow requires that Earth has a planar reference surface. They don't in any way, shape or form. Today we're going to take a look at the related claim that distances across or along Earth's surface require that Earth has an approximately planar reference surface. Oakley seems to believe that given 2 points on Earth's surface, the tangential separation between them is well defined if the reference surface is planar, but not well defined if the reference surface is curved. Similarly, he seems to think that the along surface separation between 2 points is well defined if the reference surface is planar, but not well defined if it's curved. In actuality, a long surface distance is well defined for any well-behaved surface. So let's go back to the very basic elements. The shortest distance between any 2 points is the straight line interval connecting them. If we know the coordinates of the 2 endpoints of the interval, we can calculate the straight line distance just using Pythagoras' theorem. But what if we are physically unable to follow the path between these 2 points? What if there's some obstruction or some constraint that we have to obey? What if we have to follow some arbitrary but smooth path? First of all, we parameterize the path. That is, we express the spatial coordinates x, y, and z as functions of some independent variable t. Any smooth curve can be approximated by taking a number of straight line intervals. We can then approximate the length of the curve by adding together the lengths of the intervals. The more intervals we use, the more accurate our estimate of the length of the curve becomes. So we can obtain an estimate of arbitrary accuracy by using a sufficient number of points. This is exactly how along slope distances are calculated in surveying exercises. Now let's zoom in on a single line element where the change in the independent variable is some small value, delta t. Let the length of the interval then be delta s. We can then obtain an expression for delta s by plugging the initial and end points of the interval into our distance formula. We can rewrite this expression as the square root of the sum of the squares of the increments of the individual coordinates. Multiplying by delta t over delta t, the terms inside the square root sign just become the gradients of each of the coordinates with respect to t. Letting delta t become infinitesimally small, we just obtain the derivatives of each of the coordinates with respect to t. We can then obtain the total length of the curve between these 2 points by just integrating this term. So we can see instantly that Oakley is just wrong. Given a curve of arbitrary geometry, we can well define and measure the distance along it. Let's consider a specific example. Consider 2 points joined by a circular path of radius r. The distance between these 2 points along this arc is completely unaffected by where we put the origin for our coordinate system. So we're free to choose a position for the origin that provides maximum mathematical convenience. In this case, that would be the center of the circle. Similarly, the distance between the 2 endpoints of the arc is not affected by any rotations we may apply to our coordinate system. So we're free to rotate our coordinate system so that the circular path lies in the horizontal plane z equals 0. We can then parameterize our path as shown. We can then readily obtain parametric derivatives and substitute them into our distance functional. Using the properties of the trigonometric functions, that is, that cos squared plus sine squared equals 1 for all angles, gives us a very simple form for the distance functional in this case. In fact, it couldn't be much simpler. Integrating the distance functional along the length of the arc then gives us the total distance between the 2 points along this arc. And so we have obtained the standard result, that the distance along a circular path is just the product of the radius of the circle and the angular separation between the endpoints of the path. Remembering that, as always, unless otherwise specified, we are measuring angles in radians. That's all well and good, but what happens if we're on a curved surface and we don't yet know what the shortest path is? Is there a way of finding that? In fact, there is. Finding the function that minimizes a given integral is a well-studied problem from the calculus of variations, where it has been well established that the functional that minimizes a given integral obeys the Euler-Lagrange equation. I'm not going to go into any detail about the derivation of this formula. We're just going to accept that this is a well-established result. But this might be a good opportunity to warn people that the mathematics is about to get really hairy, so buckle up. But it might be helpful to have a look at a specific example. Consider a sphere of radius r, and an arc on that sphere along which we know the change in colatitude and the change in longitude. Many of you won't have heard the term colatitude before, it's just 90 minus latitude. Mathematicians prefer to use colatitude because we're weird that way. Anyway, because we know the change in colatitude, we know the length of the latitudinal arc marked in blue. It's just the radius times the change in colatitude. We now construct rays that extend orthogonally from the vertical axis out to the endpoints of the longitudinal arc marked in blue. The length of these rays is just r times the sine of colatitude. The length of the longitudinal arc is then just r times the sine of colatitude times the change in longitude. We can now apply Pythagoras' theorem to estimate the length of the arc. We are, of course, working on the surface of a sphere, not with planar triangles, so this is just a loose estimate. However, the smaller we make the change in colatitude and longitude, the more accurate this estimate becomes, until, in the infinitesimal limit, the equivalence becomes exact. This gives us the distance functional for a sphere of radius r. This is the functional whose integral we want to minimize to find the geodesic. So to solve this problem, we just plug this functional into the Euler-Lagrange equation. And this gives us the following result. Now if we rotate our coordinate system so that the initial point of the arc lies at the North Pole, we can see that our constant of integration must be equal to 0. I will point out once again, rotating our coordinate system is perfectly valid. We can do this because doing so doesn't change the position of either of the arc endpoints, so it doesn't change the distance being measured. Anyway, our end result is that the derivative of longitude with respect to latitude is just 0, which means that longitude is just some constant value. This is the definition of a great circle passing through the North Pole. We thus obtain the result that the geodesic on a sphere is just a great circle. Now there are many easier ways to get this result. The point of doing it this way is just to demonstrate that we can find geodesics for arbitrary surfaces. There is absolutely no requirement that the reference surface be planar in order to be able to define or evaluate a geodesic function. So we've established that the geodesic on a sphere is just a great circle, and that the distance between 2 points on a great circle is just the radius of the sphere times the angular separation of the 2 points. With appropriate rescaling, the distance between 2 points on a circular arc is also just a constant times the angular separation in degrees. And this is very close to what we observe on Earth. Geodesics are very close to great circle arcs, and distances between points on Earth's surface are proportional to the angular separation of those points. I bring this up because I think this may be related to one of the less coherent things that Oakley says. He keeps on talking about linear distances. Now, as we've already noted, across any suitably smooth surface, any path can be approximated by a series of straight line intervals. But even a primary school student can work out that just because the intervals are straight over a short distance, that doesn't mean you get a straight path when you string them all together. I suspect that what's happened is that somewhere along the line, Nathan Oakley has heard someone say that on Earth, distance is a linear function of angular separation. And somewhere in the dark, feverish depths of his twisted imagination, he has leapt to the conclusion that this means that distances on Earth are measured along straight lines. But that's not what this phrase means. In mathematics, a linear function is any function in which the dependent variable is equal to some multiple of the independent variable plus some offset. This describes a line in the parameter space defined by the dependent and the independent variable. While lines in physical space are linear functions, not all linear functions describe lines in physical space. Looking at the functional form for distances across a sphere, we can see that distance is indeed a linear function of angular separation. But by definition, these are not straight line distances. So the fact that we observe an approximately linear relationship between distance and angular separation across Earth's surface is not an indication that Earth is approximately planar. It's very strong evidence that Earth is approximately spheroidal. In this video, we have shown that distances can be meaningfully defined and accurately measured along any smooth curve of arbitrary geometry. We have also shown that there exist mathematical techniques for identifying geodesic curves along any smooth surface. We have also shown that the approximately linear relationship between distance and angular separation across Earth is consistent with Earth being approximately spheroidal and is inconsistent with Earth being planar. In short, every single element of Oakley's claim is utter rubbish, completely without logical, mathematical, geometric, or evidential support, as persuasive as it might sound on a t-shirt or a baseball cap. So that might be where I call an end to proceedings today. Thank you so much for watching, I really do appreciate it. And I hope you'll join me next time when I discuss Oakley's most bizarre claim that somehow elevation distances require that Earth has a planar reference surface.